Then I have
You
to
have
make.
put 9:30 p.m.
Huh?
You have put 9:30 p.m. Is it?
Hmm. Sure, you can go live. We are live now.
But you had scheduled it at 9:30 p.m.
You have told them now, no? You have given them the time.
No,
You
but
have
I told
given.
you to
No, it
schedule
was
it at
17.
7:30.
It was 17.
7:30
You
p.m.
probably said 19:30.
No, no, it said 9:30 p.m. It said, yeah, doesn't matter. We will anyway remove the YouTube video.
They are the students are watching.
Hello, are you able to hear me? Very good. So you're able to see the slide that I've shared. Are you able to see it? Okay, fine. Then I'll start my lecture. So this is about the complex variables, and this is a subject that you're already familiar with from your BSc physics classes. So I'll go through it very quickly. So as you know that mathematicians, they developed the idea of complex variables when they wanted to solve quadratic equations like x square plus 1 equal to 0, because x square plus 1 equal to 0 has no real solution. So therefore, what they did was they essentially talked about postulating a new number iota, which is square root of minus 1, defined by them. And if this new number is postulated to be square root of minus 1, then I square is minus 1 and 1 over I is minus I. Using this imaginary number, the mathematicians developed the whole field of complex analysis so that one can write a complex number z as x plus iy for any x and y belonging to the formula. E raised to power I theta is equal to cos theta plus I sin theta, which is a very, very important formula for physics. And it's also an intriguing formula because on the right hand side, you have geometrical quantities, basically the trigonometric functions cos theta and sin theta. And of course, there is the postulated imaginary number I, while on the left hand side, you have exponential of I theta. As you know, exponential function comes as a series expansion. E raised to power x is 1 plus x squared by 2 plus x cubed x cubed by 3 factorial and so on. And exponential is related to logarithmic functions because log of e is equal to 1 or log of x can be thought of as inverse of e raised to power x. Why? Because e raised to power log x is nothing but x itself. Okay? Or log of e raised to power x again is x itself. And therefore, this formula certainly is not very intuitively obvious. But because of this formula, you can write any complex number z as x plus iy equal to some real number r into e raised to power I theta. And because e raised to power I theta is cos theta plus I sin theta, we have x plus iy is equal to r cos theta plus iota r sin theta. In other words, x is r cos theta, y is r sin theta. Therefore, the set of all complex numbers denoted as C is simply the set whose elements are of the form x plus iy, where x and y are any real numbers. From this expressions that x equal to r cos theta and y is equal to r sin theta, one can immediately write r as square root of x square plus y square and tan of theta as simply y divided by x. This follows from the expression x equal to r cos theta, y is equal to r sin theta. And because of these expressions that r is square root of x square plus y square and tan theta is y by x, one can easily derive the partial derivatives of r and theta with respect to x and y. So I leave it to you to prove that these results are indeed true. Namely, please show the results summarized in equation 74a, that is del r by del x is x by r, del r by del y is y by r, del theta by del x is minus y by r square, and del theta by del y is x by r square. Now, we also know that given any complex number z, which is x plus iota y, complex conjugate of z, which is denoted by z star, is simply x minus iy. The reason being that x and y, of course, are real number. The complex conjugation will not do anything to x and y. But complex conjugation of iota is defined to be minus iota. That is, under the operation of complex conjugation, iota goes to minus iota. And therefore, if z is equal to r into e raised to power I theta, z star, the complex conjugate of z, is r into e raised to power minus I theta. Now we embark on the topic of functions of complex number. As you know, functions are essentially mapping from one set to another set. In the case of functions of complex numbers, we are interested in mapping f from the complex plane to the complex plane. Sometimes the complex set is called complex plane because just like your Euclidean plane is characterized by r cross r, that means any point on an Euclidean plane has Cartesian coordinates x comma y. Similarly, any complex number, since it is characterized by x and y, therefore the set of complex numbers are also referred to as complex plane. A function of a complex number is a mapping from the complex plane to itself, so that for all complex numbers belonging to the complex set, f of z is a complex number. Because f of z is a complex number, it can be also written as real part of fz plus iota times imaginary part of fz, just like z is x plus iy. Any complex number can be written as real part plus iota times imaginary part, and therefore f of z can also be expressed as a real function of z, that is real function u of x comma y plus iota times another real function of z, that means v of x comma y. In equation 74b, therefore, one has expressed the mapping f of z, the complex function f of z, as the real part of the complex function plus iota times the imaginary part of the complex function. U and v, which are functions of z, that means they are functions of x and y, u and v are of course real valued function. But f of z being u plus iota v, f of z is a complex number for every z. Now we are going to talk about the derivative of f of z. How is derivative defined? Here again I have made a typo. See, there's a typographical error. Please correct it. What I meant was dfz by dz. The d is missing. So the derivative of fz, which is dfz divided by dz, is defined to be take f of z plus delta z. From that you subtract f of z and then divide by delta z. So delta f is by definition f of z plus delta z minus f of z and divide by delta z. df by dz by definition is limit delta z tends to 0. Okay. But because f of z can be written in terms of the real part u and imaginary part v, so f of z plus delta z is simply u of x plus delta x, y plus delta y, plus iota v of x plus delta x, y plus delta y. And from that you subtract f of z, which is u of xy plus iota v x comma y. And from that, and to that you divide by delta z, and delta z is delta x plus I times delta y. And doing a Taylor expansion of both u and v around x and retaining first order terms in delta x and delta y, we find that ux plus delta x comma y plus delta y minus u of xy is simply partial derivative of u with respect to x into delta x plus partial derivative of u with respect to y into delta y plus the iota, the imaginary part sitting in front of v. So iota delta v by del x delta x, and similarly delta iota times delta v by del y into delta y. Then combining the coefficients of delta x and delta y, we can therefore write dfz by dz as limit delta x tending to 0, delta y tending to 0, del u by del x plus I del v by del x into into delta x plus del u by del y plus iota del v by del y into delta y, divided, the whole thing is divided by delta x plus iota delta y. But since this is a derivative that is being taken at point z on the complex plane, you can approach z in many ways. After all, it's a point on a plane. You can approach the point z from any direction. But in order dfz by dz is a meaningful derivative, the result, which is summarized in 74C equation, their result should not depend upon in what direction you approach the point z. In particular, dfz by dz, again there's a typo here, I meant dfz by dz. The derivative dfz by dz at point z in particular is meaningful if and only if the f of z is continuous. That means the limit of f of z plus delta z going to z, that exists. And furthermore, the condition B, that the limit of equation 74z C does not depend in what manner you take delta z going to 0. So, for instance, we can first consider approaching z along a line which is parallel to the y-axis. If a line is parallel to the y-axis, that means y value is constant. Okay, sorry. If it's a line is parallel to the y-axis, x value is constant all along the line. So therefore, delta x is 0. And if you are approaching the point z along a line parallel to y-axis, only y will be changing. That means only delta y will be non-zero. And therefore, if you substitute in equation 74C, delta x is 0, then you will get the derivative to be limit delta y tending to 0, del u plus del y plus iota del v del y multiplied by delta y divided by iota delta y. And therefore, delta y will cancel. So the result therefore is, everywhere there seems to be this typo. It should be dfz by dz. Dfz by dz is limit delta y tending to 0. But because delta y is appearing in the numerator as well as the denominator, delta y will cancel. And 1 over iota being minus iota, we get the result that dfz by dz in the limit delta y tend to 0 is simply del v by del y minus iota del u by del y. Okay. While you can also consider approaching z along a line that is parallel to the x-axis. So if you go along a line parallel to the x-axis, then what it means is y is constant. Any line that is parallel to x-axis, any point on the line will have the same value of y. So delta y will be 0. Only delta x can vary. And therefore, if you substitute in equation 74C, delta y is 0, then you will get df z by dz as delta x tends to 0 is simply del u by del x plus iota del v by del x multiplied by delta x divided by delta x. So therefore, we have the result that dfz by dz as limit tends to delta x tends to 0 is simply del u by del x plus iota del v by del x. So now look at the bizarre thing that we have arrived. The same function, its derivative dfz by dz, if you approach z along a line parallel to y-axis, you get the result summarized by equation 74d, while if you approach z along a line parallel to x-axis, then dfz by dz is del u by del x plus iota del v by del x. And therefore, in order that derivative exists at the point z, equation 74d must be equal to equation 74e. But that means the real part of the right hand side of equation 74d must be equal to the real part of the right hand side of equation 74e, and similarly the imaginary part of both the equations must also match, and hence we get the equations that del u by del x is equal to del v by del y and del v by del x is equal to minus del u by del y. So by matching 74d and 74e, we arrive at the equation 75, which are two conditions in order that dfz by dz is a meaningful concept. In other words, what we have derived is the derivative of a complex function at a point z exists if and only if the equation 75 is satisfied. That means del u by del x equal to del v by del y and del v by del x is equal to minus del u by del y. These are called Cauchy-Riemann conditions, named after the mathematicians who obtained these results. Complex functions whose derivative exists are called analytic functions. All right. And you will see that analytic functions have very interesting properties. Similarly, the other term that is also used is if a complex function f of z satisfies equation 75 at a point z naught, that means if a complex function f of z is such that df by dz exists at the point z naught, then the complex function f of z is said to be analytic at the point z naught. While there are another class of functions which are analytic everywhere on the entire complex plane C. Such functions. Stated differently, entire functions are complex functions for which df by dz exists everywhere on the complex plane. Let's consider some examples. First example is the function e raised to power z. It can be easily shown that e raised to power z not only is an analytic function, it is analytic everywhere on the complex plane. That means it's an entire function. Let's prove this. After all, what is e raised to power z? e raised power z is equal to e raised power x plus iota y, because z is equal to x plus iota y. And therefore, e raised power x plus iota y is e raised power x multiplied by e raised power iy. Because why? Because any number a to the power m plus n is a to the power m multiplied by a raised power n. So e raised power x plus iota y is e raised power x multiplied by e raised to power iota y. But now we can use the Euler formula. Remember the Euler formula that e raised power iota theta is cos theta plus iota sine theta, and therefore e raised power x into e raised power iota y is e raised power x cos y plus iota sine y. In other words, e raised power z is a complex function for which the real part u is e raised power x cos y, and the imaginary part of e raised power z is e raised power x. Okay. Now let's check whether the Cauchy-Riemann conditions are satisfied. Now remember, we are referring to these calculations at arbitrary point x and y. So now the partial derivative del u by del x, which is del u by del x of e raised power x cos y doesn't depend upon x, so e raised power x only depends upon x. So therefore del u by del x will be del ex by del x into cos y, but del ex by del x is ex itself. In other words, del u by del x is u of x comma y. V being e raised power x into sine y, del v by del x is similarly v itself. Why? Because again sine y doesn't depend upon x. So partial derivative of v with respect to x is sine y into partial derivative of e raised to power x, which is e raised to power x, and therefore del v by del x is equal to v itself. On the other hand, del u by del y, now the y dependence is only there in cos y. So therefore del u by del y will be e raised to power x derivative of cos y with respect to y, which is minus sine y. So therefore del u by del y is minus of v, because v is e raised to power x sine y. Similarly, del v by del y is e raised to power x del by del y of sine y, but that is cos y, and e raised to power x cos y is u. So therefore del v by del y is u. Clearly, the Cauchy-Riemann conditions are satisfied everywhere, because del u by del x, which is equal to u, is also equal to del v by del y, which is u. Similarly, del u by del y being minus v is equal to del v by del x, which is v. So del u by del y is minus del v by del x. So Cauchy-Riemann conditions are satisfied for all values of x, y, and hence e raised to power z is an entire function. Consider another example. The other example is z star to the power n, and z star to the power n is not analytic whenever n is greater than or equal to 1. Let's prove this. z star to the power n, because z is r raised to power I theta, so z star is r multiplied by e raised to power minus I theta, and therefore z star to the power n is r raised to power n multiplied by e raised to power minus iota n theta. Again, applying the Cauchy formula, which says e raised to power minus I n theta is cos n theta plus iota sine of minus n theta, but sine of negative is negative of sine. So therefore, z star into n is r to the power n multiplied by cos n theta minus iota sine n theta. Okay. This implies for the function z star to the power n, the real part u is r raised to power n cos n theta, while the imaginary part of z star to the power n v is minus sine n theta into r raised to power n. Now, using equation 74a, what is equation 74a? In equation 74a, we have the partial derivatives of r and theta with respect to x and y. Using this set of results, one can easily show that del u by del x, because u depends on both r and theta, and r and theta both depend upon x and y. So you have to take partial derivative of del u by del x, and using equation 74a, you can prove that del u by del x is n into r raised to power n minus 1 cos of n minus 1 theta, while del u by del y is minus n r raised to power n minus 1 sine n minus 1 theta. And similarly, del v by del x, is minus n r raised to power n minus 1 sine n minus 1 theta, and likewise del v by del y is minus n r raised to power n minus 1 cos n minus 1 theta. But now you see, from these results, we see that Cauchy-Riemann conditions are not satisfied anywhere, because del u by del x is not equal to del v by del y, because there's a negative sign for del v by del y. On the other hand, del u by del y is equal to del v by del x. That shouldn't have happened. So Cauchy-Riemann conditions not being satisfied tells us that z star to the power n for n greater than equal to 1 is not an analytic function. On the other hand, z raised to power n for n greater than or equal to 0 is an entire function. For this, we don't have to do any calculation. Why? Because z raised to power n will be r raised to power I theta to the power n. All what will happen is the difference is, instead of minus, you will get plus. In other words, for z to the power n, the real part will be Rn, r to the power n cos n theta, while the imaginary part will be Rn, r to the power n into sine of n theta. So therefore, v will become negative. When v becomes negative, then as you can see, the Cauchy-Riemann conditions will easily be satisfied. That means wherever you have v, just put it negative in equation 76b. So del u by del x will be equal to del v by del y, because v is now negative. So this will become plus sign. Similarly, del u by del y, which is this expression, will be negative of del v by del x, because this sign will not be minus, will be plus. And hence, just by substituting in equation 76b minus v in place of v, we get the result that z to the power n is analytic everywhere on the complex plane, and therefore z to the power n is an entire function. Now we are going to talk about some very important results like Cauchy theorem. And for Cauchy theorem, we require certain concepts which are topological concepts. Okay? That means connectedness of a plane region. Of course, topology is a very involved field of mathematics. We are going to use only very basic ideas of connectedness on a two-dimensional surface. First, we will define what is a simply connected region on a two-dimensional surface. Given a region RSC on a two-dimensional surface, this two-dimensional surface can be the xy plane of R cross var set, or the complex plane which we are familiar with, or the surface of a solid sphere. Take a solid sphere and only talk about its surface. The set of all points on the surface of a solid sphere is called S2 by the mathematicians. Or the surface of a solid torus. Torus is when we were kids, we used to play with the ring ball. The surface of a ring ball is nothing but the surface of a solid torus. All right. So we can consider any patch or any region on two-dimensional surfaces, and this region R of SC is said to be simply connected if and only if every possible closed contour lying within this given region R of SC can be shrunk continuously to zero length without ever leaving the region RSC. So remember that region RSC is said to be simply connected only if and only if there any contour, you give me any contour, closed contour on lying in this region, which can be continuously shrunk to zero length without ever leaving the region. Okay. I will soon show you some pictures, because I realize that for complex analysis we have to draw pictures and curves in order to illustrate the points, and I soon go to the pictures. But let me first finish the written aspect first. So let's consider examples. So as you can see, that the entire xy plane formed by points whose coordinates are x, y, which mathematically it can be written, the set of all points x comma y can be written as R cross R set. If you can include all points of xy plane, then it is a simply connected set, because you take any closed curve anywhere, you can always shrink it to zero length. Similarly, the entire complex plane C, if you take the entire complex plane C, then of course any curve which is closed anywhere can be shrunk continuously to a point. Similarly, if you take the surface of the solid sphere and include all the points of the surface of a solid sphere, any closed contour, you can shrink it continuously to points. I'll soon show you pictures so that you have a good idea of what is going on. Okay. So these are the examples of simply connected set. Now let's consider what could be the examples of regions which are not simply connected. So imagine that you take any of these simply connected regions and puncture them. You create holes in them. Okay. So take a plane and take a region of the plane and remove it altogether. Then such a set, of course, from any point to another point, you can go. However, although it's a connected set, that means if you take a plane and dig out a hole, you remove a small patch from this plane, then although you can go from one point to another point along a path, but it is not simply connected. Why? Because take a curve, closed curve around the hole. If you take a closed curve around the hole, then that closed curve cannot be shrunk to a point without leaving the region, because there is a hole. If you want to shrink it to a point and the curve goes around the hole, if you're trying to shrink it to zero length, you have to leave the set and enter the hole. That means imagine that you have a landmass, and within that landmass there is a pond which contains water. Then if I give you a rope, closed rope, which is lying all around the pond, and ask you to shrink the rope, okay, contract the rope, then eventually the rope will have to enter the pond. And hence, the pond doesn't belong to the land, and therefore the land part is not simply connected. Although it is connected, you can go from any point on the land to any other point, but it's not simply connected. That because there is a class of closed contour which cannot be shrunk to a point. Okay. So whenever a simply connected region, from that you remove a simply connected portion, then the resulting region is no longer simply connected. Surfaces which are not simply connected, they are called multiply connected regions. And one of the examples of a multiply connected region is the surface of the solid sphere. And I will show you pictures now from which you can see that indeed the surface of a solid sphere is not a simply connected surface. Now what I will do is I'll stop. Okay. So now I will share some of the pictures. Okay, I can see that there is a question. Before I share the pictures, Vinu has asked, what exactly is meant by shrinking the contour? What it means is that your contour, think of the contour as a highly stretched rubber band, and it is maintaining a long length because you have stretched it. But release the force, that is keeping the rubber band stretched. Then the rubber band will shrink. So imagine that you have a table and the table has a small pool of water because you have spilled water on the table. And the water has collected in a small region on the surface of the table. Now, everywhere else, you can take a stretched rubber band and let it shrink by because of its own tension. Everywhere else, it'll shrink without leaving the table. But take the rubber band around the pool of water, stretched rubber band, and now release your force. The rubber band will start shrinking, but then it'll shrink and leave the table and enter the water pool. So, therefore, now you know that the water pool, if you don't consider that part of the water pool to be the part of the table, the presence of the water pool has made the table no longer simply connected. All right, now I'm going to share with you the pictures. So Rajat, just wait, I will share the picture. Are you able to see the picture? Is everyone able to see the picture now? All right. So here, for example, in the complex plane, if I take this region RSC, this region which is shaded, these horizontal, these lines are shading this region RSC. This region, you take any closed contour and you can shrink it to zero length. Similarly, if you take the surface, yeah, let me try to zoom. Yeah. Due to some reason, the zoom is not working. I'm not able to increase the size. I don't know what to do. Yeah, I'm not able to zoom it. Yeah, I tried maximizing, but it went off. I don't know what has happened. No, there's some problem by sharing the picture.
स्क्रीन शेयर तो चला गया, उड़ गया।
नहीं, स्क्रीन शेयर वही तो मैं ये पिक्चर शेयर करना चाहता हूँ।
रीडू द स्क्रीन शेयर।
हाँ, वही करूँगा।
Sometimes it doesn't show. You're not finding it.
Yeah,
Then you do
finding
whole
it.
screen share otherwise.
No, it's not happening. Here it is showing, but
Wait. What are you doing? Screen share
it's
पे
not
इसमें नहीं है।
showing. That is the problem.
Where is your pop? Where is your
Here it
PDF?
is. Here it is. Yes.
It is in the same one, huh?
Mail.
So you go here, but
Yeah,
actually,
अब आया शायद ना।
either application window or go to Chrome tab.
हाँ, क्रोम टैब में शायद आ जाएगा ये।
No.
आ जाएगा।
But on Gmail it doesn't show
Okay,
properly.
now it shows. Yeah.
It doesn't show properly, no?
Yeah, are you able to see it? Okay.
The clarity will not be good.
Yeah, you can see it now.
Better would be to download it. Download.
No. That's we download. Okay. Now you can see it. Are you able to see it now? Right. Good. So now you can see that if you take a small patch in the XY plane, the shaded patch, take any close contour, it can be shrunk to a point, all the time staying within the shaded patch. Similarly, take the surface S2, the sphere surface. Take any close contour anywhere on the surface. You can go from a larger contour C1 to a smaller contour C2 and keep going and shrink it to a point without leaving the surface. Okay. Now, let's take the example of multiply connected region. In the multiply connected region, now you see that take a square region and cut out a hole. If you have a square region on a plane and you remove a portion, this is the hole. Of course, away from the hole, you can take any contour, shrink it to 0 size. But that doesn't make the square with a hole as a simply connected set, because there are contours which cannot be shrunk to 0 size without leaving the square with the hole. Example, you take this contour and try to shrink, and soon you will see the moment the boundary of the hole, you touch the boundary of the hole, further shrinkage will take you out of the region. It will go into the hole, but that region doesn't belong to the set. So this set is not simply connected. Similarly, consider a torus. Torus is like your ring ball. So take a solid ring ball and the surface is T2, it's called T2 or the torus. You can shrink any contour which is on the side and you can shrink it to a point. However, consider a contour which goes all around on the surface of the torus. That cannot be shrunk to a point, because you try to shrink it, soon you will enter this rim. And furthermore, if you try to shrink it, you will go out of the ring ball. So these are examples of not simply connected region. Okay. Now let's go to another uh, concept in complex variable, which is the integration of a complex variable. Okay. So are you able to see this slide? Zoomed slide? So now we will talk about a complex function f of z, and we will talk about integrating the function from point z1 to point z2, okay, along a path p. Now obviously, on a plane, when you talk about integrating a function f of z from z1 to z2, the integral will depend upon which path p you have chosen. And that's the reason why you have to specify the path beforehand so that one can evaluate the integral of the complex function. And how is integration defined? What you can do is you can take this path p from z1 to z2. You choose a particular path and divide it into n equal segments. That means this entire path has been divided into n equal segments, so that distance between any two neighboring point is delta z. Then the integral of f of z dz from z1 to z2 is defined to be summation from z equal to 1 to n fzz into delta z. That means this point, this is z1, this point is z2, this is z, sorry, this point, I should have called za to zb, but doesn't matter. You're moving from one point to another, evaluating the function, multiplied by delta z, and take the limit that delta z goes to 0. That means n goes to infinity. So n goes to infinity and delta z goes to 0. But now we also know that f of z is given by the real part plus iota into the imaginary part. And similarly, delta z will be delta x j and delta y j. So your delta z will have components delta x j plus I delta y j and so on. Okay? And therefore, the integral z1 to z2 fz dz over the path will be the limit delta xj going to 0, delta yj going to 0 of fz. Fz is what? Uxj comma yj plus iv of xj comma yj into delta xj plus I delta yj. Okay. Now you multiply. When you multiply, iota into iota, of course, will be negative. And therefore, the first term will be a real quantity, u of xj comma yj into delta xj. The iv times I delta y, there will be a negative sign, but that will be also a real term. So therefore, minus v into delta yj. But there is a imaginary part which is v into delta xj, v into delta xj. Another imaginary part, u into delta y. So u into delta y. Therefore, in the limit that delta xj and delta yj go to 0, this integral will be nothing but integral uxy dx minus vxy dy, while this part will be iota integral vxy dx plus uxy dy. This is like doing a contour integral on your plane, and you have learned how to do a contour integral on a plane from your BSc days. So suppose I now treat the xy axis to be the usual Cartesian xy axis, and I'll call u to be the x component of a vector field A and minus v to be the y component of the vector field A. Similarly, another vector function capital V, v is the real part, while u is the, sorry, not a real part, v is the x component of the vector B, while u is the y component of the vector B. And what is dl? dl is a tiny vector whose x component is dx and y component is dy. Okay? Now it is very easy to see that A dot dl, when you take dot product of A dot dl, you will get this equation. Why? Because I and j are orthonormal vectors. So u into dx, you will get u into dx, minus v into dy, minus v into dy. Similarly, b dot dl, b vector dot dl will be x component into x component, v into dx, and similarly u into dy. So therefore, the integral fz dz along the path P is nothing but integral A dot dl plus iota into integral B dot dl. Okay. Now, supposing this path is a closed contour, if you are integrating over a closed path, all right, now consider the path to be a closed path, a path like this, let's say. You are taking the complex plane, you have chosen a closed contour C, and you are integrating along anti-clockwise direction. Then obviously, the contour integral f of z dz will be just like what we showed, A dot dl along the C in the anti-clockwise direction plus I into B dot dl along the contour in the anti-clockwise direction. In your BSc days, you know that A dot dl over a closed curve due to Stokes' theorem is given by curl of A dot dA. What is dot dA? Dot dA is the surface element on the region bounded by the contour C. That region can be called capital S. dA is a small area element and the direction is perpendicular to the surface. In this case, the direction of dA is along the z direction because we are talking about y and x. All right. Similarly, similarly, B dot dl can be written as curl of B dot dl. And how do we take the curl of A? Curl of A is simply the cross product of ijk, taking the determinant of ijk, del by del x, del by del y, del by del z, ax, ay, and 0. And you can immediately see, because A and B, they depend upon only x and y. There is no z dependence. And therefore, only term of curl of A that will survive is the z component. Here I have shown you the full calculation. When you take the curl of A using the determinant, then you will get the result as minus I unit vector. This is unit vector, not iota, but minus I unit vector del ay by del z plus unit vector j del ax by del z. But ay doesn't depend upon z, ax doesn't depend upon z. So these two terms will be 0. And you get k unit vector times del ay by del x minus del ax by del y. But what is ay and ax? Go back to our previous result. A was u unit vector I minus v unit vector j, while B was unit vector I times v and unit vector j times u. So therefore, when you use that, you get the result that curl of A is k unit vector into minus del v by del x minus del u by del y. Analogously, curl of B will be unit vector k, just substituting B in place of A, you'll get again the same result. Instead of del ay by del x, you'll get del by by del x. Instead of del x by del y, you'll get minus del b by del y. But now, by and bx, what are by and bx? Bx is v and by is u. And therefore, you get curl of b to be del u by del x minus, because of this minus sign, del v by del y. Now you appear to witness a very interesting result. That is, suppose your f of z is an analytic function. If it's an analytic function, Cauchy-Riemann condition says that del u by del x must be equal to del v by del y. That means curl of b is 0. Similarly, the other condition is del v by del x should be equal to minus del u by del y. That means this is 0. So therefore, curl of A is 0, curl of B is 0 for an analytic function. And therefore, contour integral of f of z dz along a closed contour which has a region bounded where curl of A must be defined, curl of B must be defined in order Stokes' theorem is valid. Only when curl of A and curl of B is everywhere obtainable within the region, only then I can apply the Stokes' theorem. And therefore, your function must be analytic everywhere within the region bounded by the closed contour C. And in that case, what we have just now showed, because curl of A is 0, curl of B is 0, as f of z is analytic, we have got a very important result. And what is that result? That if f of z is an analytic function. That means it's analytic everywhere within the region bounded by the closed contour C, then the integral over the closed contour C of such an analytic function is 0. This is a very, very important result, and it has huge application in evaluating integrals exactly. So on Thursday, I will take few examples where I'll use this Cauchy theorem to obtain exact and analytic expression for integrals. Okay, I'll stop here. If there are any questions, you can ask. You have been given quite a few problems in complex variables, and all these results that I discussed today, you have to use them to solve some of the problems of your tutorial set. Are there any questions? Yes, so Rupesh, good question. We have already proved that if the group is abelian, then we have proved this result, that if a group is abelian, then any representation in dimension greater than or equal to 2 has to be reducible. So if you know that your group is abelian, then any 2, 3, 4 dimensional matrix representation is going to be reducible. On the other hand, if your group is not an abelian group, then of course you have to take the higher dimensional matrix representation and obtain the eigenvalues and eigenvectors to construct the unitary matrix that can bring your matrices to block diagonal form. So that has to be done. Is that clear, Rupesh? I hope you got my answer. Most welcome. Are there any other question? Yeah, so Sahil is asking about simply closed curve in orientation. Well, I hope you're not asking about whether the space itself is orientable. That's a separate thing. Like, for example, the Mobius strip is not an orientable set. But what you're asking is the directionality. That means if I take a closed curve, how I go, do I go clockwise or I go anti-clockwise? Now, in complex variable, the convention is when I write integral f of z dz with a contour, I am going along anti-clockwise direction. So therefore, if you integrate f of z dz along the same contour but in a clockwise direction, you pick up a negative sign. All right. I hope I have answered your question, Sahil. Tanya, yeah, if the matrix is already in the diagonal, all the matrices representing all the elements of a group, if they are all in the diagonal or block diagonal form, then you already know that it's in the form of irreducible representation. Yeah, Rajat, I will post these notes. I will soon do that. Very good question, Vinu. Uh, she is asking whether a closed contour can cross itself. Yeah, you can think of a closed contour which crosses itself, but then such a closed contour, you can think of it as two contours which are intersecting at a point. All right. So a figure 8, for example, the figure 8 is a contour which crosses itself. But the figure 8 can be thought of as two circles which are touching at a given point. Well, Sajal, I have already shown what is the geometrical meaning of a irreducible meaning of an irreducible representation. When you have irreducible matrix representation, then the action of the group, it is independently done on the subspaces of your vector space, which is the representation space. All right. So, for example, consider the U1 group. U1 group, when you considered the two-dimensional real vector space, it was of the form cos theta sine theta minus sine theta cos theta. But this was not of the diagonal form. So what you did was you said that let me go over to a two-dimensional complex vector space and diagonalize cos theta sine theta minus sine theta cos theta. And what did you get? The diagonalized form of the matrix representation was e raised to power I theta in the diagonal and e raised to power minus I theta, the other diagonal element. The off diagonal elements were 0. What did it mean geometrically? What it meant was that your column vector V and W, let's say, complex values V and W, it's a column vector. Your irreducible representation acts differently for different elements of the two component. For the upper, that is V, when the group U1 acts, it multiplies by e raised to power plus I theta. So V prime is e raised to power I theta V. While W goes to W prime, which is e raised to power minus I theta V. So therefore, your subspace, one-dimensional and one-dimensional subspace of the two-dimensional vector space is transformed differently by the action of rotation by theta. Okay? Have I answered your question, Sajal? I've got the general result for any arbitrary group when you have the irreducible representation D1G, D2G, D3G, etc., then each block diagonal element, they act on a subspace of the representation space independently. I don't understand the question, Sahil. Z plane can be on a sphere. What do you mean by that? The complex plane has points x, y, but you can do a projective mapping. It is normally done to see where is the point of infinity. So what you do is you think of a sphere which is resting on the complex plane and draw straight lines from any point of the complex plane joining the north pole of the sphere. Okay? And wherever the point, the straight line intersects the sphere, that point is the representation of the complex plane on this Riemann sphere. The sphere is called the Riemann sphere. So therefore, the point at infinity, all the points which are at infinite location from the center of your complex origin, complex plane origin, all of them, they get mapped to the North Pole. While the South Pole, okay, is mapped to the origin. So this Riemann sphere construction tells you that the complex plane points can be mapped using this projection mapping to a Riemann sphere where all the points which are at infinite distances from the origin, they get mapped to the north pole of the sphere. Sahil, geometry is not involved. I have not talked about Pythagoras theorem or anything. So our complex plane is simply a plane where every point is represented by the real part x and the imaginary part y. What you probably mean is the topology. As I said, the sphere topology S2 is different from the topology of the plane. So when I talked about the mapping of complex numbers onto a Riemann sphere, it was a mapping from both are two-dimensional. The plane is two-dimensional. The surface of the sphere is also two-dimensional. But we did not consider the geometry. What we said was we considered a mapping from points of the complex plane to points on the Riemann sphere, and therefore no geometry was involved. We were basically having a mapping from one topological space to another topological space. Dibojyoti, the lecture is already in the YouTube, but the written part, my PDF, as well as the pictures, that I will post into the Microsoft Classroom. Rahul, yes, you can also think about derivative of a function of z star with respect to z star. You can do that. It's a good question. You can, but you have to follow the same route. You have to say f of z, d of f of z divided by d of z star. What does it mean? You can do that. And the derivative can be found using the same thing that I discussed. But obviously, if your f of z is not a function of z star, df by dz star will be 0. While you can think of a complex function which is a function of z and z star, then df by then del f by del z star, you have to talk about partial derivatives. Okay, you can obtain partial derivative with respect to z and z star. But in our lecture, we will not consider functions of z and z star. We will only talk about functions which are dependent only on z. Yeah, so Sajal, your question, a cylinder whose base is there, but you have removed the top. And if you are only talking about the surface of the cylinder, not the interior portion. So it's a two-dimensional surface. As you can see, if you just take the wall of the cylinder and the base of the cylinder, the, the top has been removed. Such an object is topologically same as a disk. You can map this cylinder, surface of the wall of the cylinder along with the base. You can stretch it out to form a disk. And the disk is certainly simply connected. Okay? While, so the disk, that means the cylinder where the walls are there, the base is there, but the top, the roof is not there, such a surface is simply connected. On the other hand, the cylinder, which is having both base as well as top surface of the cylinder, this is not simply connected. Why? Because a contour which is going around the cylinder, that cannot be shrunk because there is a two-dimensional surface. A contour around the cylinder, oh no, it can be shrunk. Sorry, that is also simply connected. It can be shrunk because you can go to the top. You keep on sliding the contour and go to the top, and the top part you can shrink it, or bottom part you can shrink it. So a cylinder which is having both base as well as the top, that topologically is same as the surface of the sphere. And surface of the sphere is simply connected, and so is the surface of the cylinder with both top as well as bottom. Both are simply connected. While a cylinder whose top has been removed, only the walls and the base is there, that topologically is same as a plane or a disk, and that is also simply connected. But the cylinder without the top is a disk and it has a boundary, while neither the S2 or the cylinder with both top as well as bottom, they have boundary. They don't have boundary. So that topologically they are distinct objects. Is that clear, Sajal? So you can draw the pictures of cylinder with a base without the top. You can see that you can stretch out and it just forms a disk. While a cylinder which has both top as well as the base along the wall, that is topologically, it can be deformed to just the surface of the sphere. While if you take the surface of the sphere, make a hole, that means you remove one point, then a sphere with a point removed becomes your cylinder without the top, or in other words, it's like a disk. It's topologically same as the disk. Are there any other question? I hope my internet at home improves so that we can go back to the Microsoft Classroom. Due to some reason, uh, Microsoft Classroom requires much more bandwidth. Rahul, in order that a derivative df by dz exists, then the derivative should not be dependent on how I am taking the limit to reach the point x. It is same even in the case of real functions. df by dx, when you take delta f by delta x going to 0, you should be able to approach the point x naught from left side or the point from the right side. But if your function f to begin with is continuous and it is differentiable, you can easily show that it doesn't matter whether you're coming from the left side or the right side. But in the case of complex function, because now you have a two-dimensional plane, and therefore when you're taking df by dz, you have to be sure that the derivative makes sense no matter in which direction you approach the point z0. And the moment you give the constraint that df by dz should be independent of how you approach the point z0, you obtain the Cauchy-Riemann condition. All right, if there are no more questions, then I will end the broadcast. I hope the internet at my place improves so that we can go back to the Microsoft Classroom lectures. Okay, so take care. Good night. I will end the broadcast now.